Hello everyone, I welcome you all to the next part of the circles, and today we're gonna start with angles subtended by an arc on a circle. Okay, we have already seen angles subtended by a chord of a circle, and today we would be starting with angles subtended by arc of a circle. Now I hope you know the difference between arc and chord. Okay, if two chords of a circle are equal, then their corresponding arc are congruent. Okay, why so? Because if chords are equal, then we have already learned that the distance from the center and hence the arc they would be creating would be of equal area. And equal area and arc would be congruent. Okay, if two arcs are congruent, then their corresponding chords are equal, just vice versa. Okay, angle subtended by an arc at the center is defined as the angle subtended by the chord at the center in the sense that minor arc subtends the angle and the major arc subtends the reflex. Okay, so I'll be just explaining you this whole thing in a very easy way. Okay, how does the arc is subtending angle at center? Maybe we can take PQ as an arc, but we can also take P and Q joining and a line segment being a chord. So it's the same thing. Okay, we just have a different nomenclature to it, but it's nothing different. PQ can be created as a chord, but the boundary conditions or the arc can also subtend an angle itself. Therefore, the angle subtended at the minor arc PQ at O would be POQ. Okay, and the angle subtended by the major arc PQ or the outside part would be reflex at O and POQ. Okay, so congruent arcs of equal areas of a circle subtend equal angles at the center. Okay, so the angle subtended by an arc at the center is double the angle subtended to it by the remaining part of the circle. So suppose that in figure 1 it's given PBQ. It would be the minor arc subtended area. And what's reflex? PAQ. So PAQ would be half of PBQ. That is what it's proven. Okay. Now, given an arc PQ of a circle subtending angles POQ at center and PAQ at the boundary. So, arc PQ is minor, arc PQ is semicircle, and arc PQ is major. There are three conditions possible, and all the three are drawn in front of you. Now, what if we consider case 1? Join AO, extending it to B. Correct? In all cases, BOQ. What is angle BOQ? It will be equal to angle QAOAQ plus angle AQO because exterior angle is equal to interior opposite angle sum. And similarly, this can be proved that OA is equal to OQ since the radius of the circle, hence both the angles are equal and hence they are half. So similarly, the other side can be proved, and when we combine the two conditions, we can prove that the angle subtended by an arc at the center is double the angle subtended by the arc at the remaining part of the circle. Okay, so this is a theorem used. Angles in a segment. Angle in a same segment of a circle are equal. So, what is segment? We have already learned. So, they are when forming an angle. Then, if the angle in the same segment of a circle would be equal. This PQ is a segment, and we have created two angles, PAQ and PCQ. Both are of equal width. Okay. So, how to prove that? We have already used the extended angle of an arc. We can just similarly use that. Okay, angles in a semicircle. A circle with center where PQ is a diameter and angle PAQ is the angle of the segment which is semicircle, then angle PAQ would be equal to half of POQ would be equal to 90 degrees. So, angle in a semicircle is always 90 degrees, and this is another proof which is very easy and same as angle subtended by arc. Okay, now what are concyclic points? If a line segment joining two points subtend equal angle at two other points lying on the same side of the line containing the line segment, the 4-line or the 4-point line on a circle, that is they are concyclic. Okay, so prove that AB is a line segment, correct, which subtends equal angle at 2 points C and D because angles subtended by a same segment are equal. Okay, now to show that ABCD lie on a circle, let us draw a circle through ACD. Okay, suppose it does not pass through D, then it will intersect AD at a point, suppose E dash. Okay, now E or E dash. If points ACEB lie on a circle, then ACB would be equal to AEB. Angles in the same segment of a circle are of equal. But ACB equal to ADB, hence prove that ADB, yeah, E and D coincide. Hence D lies on a circle. So they are concyclic. I hope this is clear to you. The proofs you don't need to remember, which are very tough for you. You just need to remember the theorems for the questions. But I hope I have made easy for you. What are cyclic quadrilaterals? We would start with that. The sum of either pair of opposite angles of a cyclic quadrilateral is 180. First of all, cyclic quadrilateral means nothing but a quadrilateral inside a circle or circumscribed by a circle. So their sum is 180 degree. A circle with center O and quadrilateral ABCD is cyclic. Okay, so we have already proved how to do that, because angle subtended by an arc at the center is double the angle subtended by the same arc to the remaining part. So this can be proved very easily by that. Okay, so we can just prove it that the angle sum BCD plus BAD would be equal to 1. Okay, so 360 degree would be the sum. Pair of opposite angles would be 1. Now, we have already seen that. Let us draw a circle passing through ACB and how it will extend to E and then AD and E will coincide. So we can also prove that quadrilateral ABCD is cyclic. And this cyclic property is already defined by concyclic points. Correct? Okay. Now, question time. AB is diameter of a circle and CD is chord equal to the radius of the circle. Just keep in mind, it's equal to radius. It's already given. AC and BD, when extended, intersect at point E. So we need to prove that AEB is 60 degree. I'm telling you, this question is really, really easy. So just pause me out and try it by yourself first, and you would be able to prove that. Do it. Okay. I hope you have attempted by yourself first. If you have concluded how to find out, very good. If not, don't worry, I'll just solve it for you. Okay. So, firstly, what is given to you? CD is chord of equal to radius. Okay. So, CD and CO, we already know it's the radius, and OD is the radius. So, which means that OCOD. Okay. All the sides are equal. So, this triangle is equilateral. Correct? So first conclusion which is given in the question we have drawn. So equilateral triangle sides are equal to 60 degree. Correct? Just keep in mind. Okay. Now, AB is diameter of the circle and hence the semicircle suspends angle 90 degrees. So right angle. We have already learned this property. So being that, this would be equal to 90. Okay. And this concludes that this angle would also be 90 degrees. So angle ECB would also be equal to 90. Correct? Now, just pay your full attention to here, this angle. This CD extends angle at a center, which is A, and angle at the remaining part, which is B. And we have already learned the property that angle subtended by the same chord to the center is double to that of the remaining part. So A angle would be equal to 2B. And we already know A is 60 degrees. So which leads to B being 30. Okay. Now we have already found the angle B, which is, I am just naming it here, AEBC or DBC, we can also name it. So we already know the angle sum property of a triangle ECB, which is 90 degree, plus angle EBC plus angle which we need to find AEB is equal to 180 degree. Correct? Just replace 90 here, 30 here. So what you will get? AEB would be equal to 60 degree. Hence proved. Correct? Okay, so I hope the solution is clear to you. If not, just look how we have derived the conclusion. Correct? Okay. Now, next question. ABCD is a cyclic quadrilateral in which AC and BD are its diagonal, and we have been given two angles. We'll just name it here. Okay, DBC. This angle we have been given 55, and another angle BAC. This angle we have been given 45. Now, what you will do? Pause me out and try to find angle BCD. It's very easy. I'm just telling you. Use the theorem that opposite sum of a cyclic quadrilateral angles sum up to 180. Okay, so just do it. I hope you have tried it by yourself first. If you have got it, very good. If not, just look at how we'll do it. C. DC is the same chord. So that we have already learned that the same segment extends equal angle to the circle boundary. So this angle would also be 55. Okay. So now we know that angle this angle and this angle, which we need to find. BCD plus angle ABD would be equal to 180 degree. We have already learned that cyclic quadrilateral opposite angles sum up to 180 degree. So we need to find this, and what is this? 55 plus 45. Okay, we can name it X, suppose, and it is equal to 180. So what would be X? What is 55 plus 45? 100, 100 and this 180. So 80. I hope you have got your answer. Correct? Okay. Next question. Two circles intersect at 2 points A and B, and being that AD and AC are diameters of the two circles, prove that B lies on the line segment BC. Just pause me out and try it by yourself first. Okay. I hope you have tried it out by yourself first, and if you get the answer, very good. If not, just look at here. Okay, we have been given that AD is a diameter, and you have already know that. Just forget about the other circle. We are seeing C1. Okay, so from C1 we concluded that this angle, suppose we name it as 1 and this angle we name it as 2. Okay, so from the diameter or the semicircle which forms an arc to the half part is 90 degrees. So we already know that angle 1 is equal to 90 degrees. Okay, and from C2 we know that angle 2 is equal to 90 degrees by the same property. Semicircle extends right angle. Correct? Okay, now just combine both. What it states? 180 degree. And what does it state? It states that linear pair exists. And I hope you know that linear pair happens only in line, which means that ABC is a line, and hence B lies on the line segment BC. So this is proof that B lies on DC. Correct? Okay. This question was easy. Prove that quadrilateral formed, if possible, by the internal angle bisectors of any quadrilateral is cyclic. How to prove that? Just pause me out again and use your brain. I hope you have tried it out, and if you have concluded, very good, because this question is a little bit tricky. Never mind, we'll just try to solve it. Okay, just come with me and see what I'm doing. This angle is equal to this angle because it's already said that internal angle bisectors, and this angle is equal to this angle. So we can say that this is half angle A, and we can say that this is half angle B. Okay. Meanwhile, you can do it from here also. This is half angle D, and this is half angle C. Okay. So we also know that angle, suppose I am naming it as A, this is B, this is C, and this is D. So we also know that angle A would be equal to angle D by vertical opposite, and angle C would be equal to angle D, both by vertically opposite. Now, what would be angle B? Angle A. And what would be angle A? 180 degree. Because what is the triangle property sum? 180 degree minus this angle minus this angle. So minus half angle A plus angle B. Similarly, angle C would be equal to 180 degree minus half angle C plus angle D. Okay. So when we add B plus C, if it is 180 degree, then the AFGH is cyclic quadrilateral, because we already know that cyclic quadrilateral has a property that opposite angles sum up to 180 degree. So let's see, it is there or not. It will be 360 minus half of A plus B plus C plus D. And what is A plus B plus C plus D? It's sum of equilateral, quadrilateral, ABCD. So it's already 180, correct? So 360 minus 180 is 180. Hence prove that, similarly you can show that for him. Hence prove that EFGH is 180. No, it's cyclic, correct. F and H would also be 180, because if other pairs are 180 sum, then the remaining would be 180, because sum total sum is 360. Okay, I hope the question is clear to you. This question was a little bit tricky. If not, just go through again and we'll wrap up here. From the next part, we will be quickly revising all the concepts that we have done. Thank you so much for attending my lecture.